This is part 5 in a series of videos in which I am designing a replacement for the Fluke 9010A cassette drive. So the idea is to use a microcontroller, hook it to a memory device and essentially duplicate the functionality of the cassette drive from the perspective of the 9010A. So in other words, being able to write the memory contents from the 9010 into a memory device, and the reverse, being able to load programs from a memory device into the 9010. I've done quite a lot of work so far, and I've got the general design sorted out, how I'm going to go about this. So it will use some very small, very cheap memory cards to essentially replace the cassettes, and they will plug into the controller, which again will be quite low cost. It's just going to use a small quad flat pack microprocessor. So I've been going through the general design, and this is actually an extra video that I had not intended to make. I've been going through the firmware that's in the 8041 controller on the cassette drive, and I've been reverse engineering it. I've pretty much done that now, so I've gone right through this entire source code, and I was going to go through this and the general design of the replacement device in this video, but I've decided to make this an extra video, and the reason for that is I've been discussing over the last few days the repair of a 9010A with someone that contacted me, and he's been trying to repair both the pod for the 9010 and his second 9010A. And one of the things I found when repairing these units and other units like this is the faults you find can be a bit unexpected and a bit frustrating to find. If we go back 40 years, then designing computer systems was very different from what it is now, and a lot of the time was spent in trying to figure out how to make the devices behave themselves, whereas these days it's very much easier. Generally you just plug them together and you just need to sort out your firmware and you're away. That wasn't the case back when devices like the Fluke were being designed. That said, the 9010A has a design characteristic that I think makes it a very poor design. And overall it's a good design, but there's a particular characteristic. Now, when you design a microprocessor system, what you normally have is your central CPU, and one of the first things you do when you're working out your design is you insert buffers between the CPU and your main bus. So for example, your data bus would pass through a bidirectional buffer, and then you would generate an external data bus, and that is what you would hook for everything else to. So all your ancillary circuits would be branched off this, possibly through their own buffers as well. Unfortunately, the Fluke isn't like that. It's got the microprocessor, and then its central bus is distributed to everything else, even this cable. So this cable actually connects directly to the data bus on the CPU, which makes it a very poor design, and it generates real flaky behavior, and I wanted to demonstrate that in this video. So if you are trying to fault finding on something like this, and also if you want to design an add-on, then there are some pitfalls that you really need to be aware of. And as I say, that was the idea of adding this video to the series. So what I have here is the general layout for the drop-in replacement for the cassette. This isn't the final device lineup. I use dual devices when I'm developing, just because it's easy to breadboard them and I don't need to use adapters and the like. And then what I'll do is replace this device with a surface mount version when I come to designing the actual board. What I'm doing here is kind of proof of concept, and also designing the firmware that goes in the processor that will duplicate what's in the cassette drive. I'll come back to the firmware in the next video. What we'll do here is look at the issues you can have if you just try and do a simplistic approach to hooking up something like a microcontroller. Now this microcontroller does have some test code in it, very basic test code, and really all it's doing at the moment is configuring the ports on the device and then looking for a certain value coming in from the data bus from the 9010. However, I wanted to show what happens if you don't take proper precautions and you don't design these things properly. So I've got this plugged into the Fluke. I'll try powering up the Fluke. You can see the display. As you can see, the Fluke does not start up. If I unplug this cable, then it will start up. Or if I unplug this wire, which is just coming from data line 0, the other data lines are not connected, I'll power up the Fluke and you can see the Fluke now comes up fine. It's not a fault with the PIC, and if we just demonstrate that, if I take a 100k resistor and plug that into this pin on the PIC, we can see the yellow channel on the scope, and if I scope the pin on the PIC and then touch the other end of the 100k resistor, you can see that the pin is floating. There's nothing, it is set as an input, so it's not a fault there. It is fully floating, it's drawing almost no current, and yet if I connect the data line, this doesn't go anywhere else, it just comes down the ribbon cable to here. But if I try attaching this to the PIC, the Fluke will start acting in a very flaky way. It might boot up sometimes, it will crash, it will do all sorts of weird things. And you can see what's going on if we just connect the scope probe to the end of this cable and look at the signal. I'll just turn the level up. So the signal doesn't look too bad there, but if I put my finger on the cable, you can see how the signal level is dropping right down. It's dropping by over a volt, and that's just me loading up the bus. Now of course it won't do this if I touch the same conductor on the PCB. This is just one of the issues you get with older design devices. They do not like weird loads on them, and it's very similar with a cassette drive. What I found when hooking up the logic analyzer is I had to be very careful how I hook this up, otherwise the Fluke would not start up. And so, in other words, I need to be very careful when I design this to make sure that I don't end up with a device that when you plug it in, it's going to stop the Fluke from powering up or booting up or even kill it completely and damage it. And by the same token, if you're trying to fault find on one of these, then just look at the bus signals. You'll find that although the bus signals may appear to be okay under certain conditions, if you try different things, then you might find that the bus signals are not what they should be, simply because there is no buffer between the CPU and the rest of the system, and there are quite a few things attached to that bus. So what we have to do to avoid any issues is of course use a buffer. So all the lines from the Fluke, we need to put a buffer between them, one for the input channels and one for the output channels. So these are the 4 control lines, so I'll put those on the input of the buffer. We need to configure the buffer. So this is a 74LS245, so we need to get some power going to it. And incidentally, this is powered from the Fluke as well, so it's all connected through the same cable. And a ground. And then because we want to send data from bus A to bus B on the 74LS245, then we need to set the direction control bit to high. So that's the direction, and we need to set that to a high level. And because this is a kind of a permanent buffer, we don't need to enable or disable this particular one. We do on the one where we're reading data or sending data back out to the Fluke, but I'll come to that in another video once I've got this design sorted out. This video is just about the things we need to watch out for, so we just need to permanently enable this particular buffer, and then what we can do is hook the same line we were having a problem with to the input of the buffer, and then all that's left to do is to connect the output across to the PIC. Okay, I'll connect both channels of the scope. So channel 2 is the incoming data, and channel 1 is the data coming out of the buffer. But also, more importantly, we now have this connected through to the PIC, and we need to see if the Fluke will still boot up, which, as you can see, it does. Not only that, but if we do a single shot capture on the data, then the yellow trace at the bottom is the data coming out of the buffer, and you can see that's nice and clean, there's no issues with that whatsoever. But the blue trace at the top is the data coming from the Fluke. And all this multi-level switching is caused by the various devices in the Fluke taking turns on the bus, and as I say, that's why you should not really connect your CPU directly to the data bus. That's the main data bus. Yes, I have tried a new CPU in this. I did have to repair this when I got it, so I went through and tidied up the signals as much as I can. I've mentioned in previous videos that quite often ICs don't just fail, they start to lose their performance, and that's what generally happens with a Fluke like this. It ultimately will stop booting up, or you'll find it operates in a very flaky way, and that can be any of the devices attached to the data bus. If they're getting a bit lazy, then it can either cause the Fluke to give you false test results with a pod, it can fail pod testing, or it can just completely fail to boot up, or it'll get weird characters, or it'll start booting up and not complete. And quite often it's not a completely failed device, so it can be quite difficult to track down the fault. But the best thing to do is get the scope on the data bus and the address bus and the control lines, have a look and see if the signals you are getting look the way they should. If they look like the blue trace at the top, then obviously you need to try to tidy that up a bit if you can. But if you are going to do some work on these and make your own accessories, then you must have an input buffer between the Fluke and your own device, even if it's just an input to a PIC or something like that. If you don't do that, then as you saw, the Fluke isn't going to behave itself, or your device will be very flaky in operation and keep crashing and causing all sorts of problems. This doesn't just apply to the 9010, this is a common problem with almost every piece of old digital electronics, and it's something you need to be aware of if you're fault finding on them. Quite often you'll find swapping out a device will fix a apparently serious fault, even though that device may then test good in an IC tester. So hope you found it interesting. It was just an extra video to show why certain aspects of this design will be the way that they are, why there will be buffers between the Fluke and the memory device, and if, as I say, if I didn't do that, almost certainly it wouldn't work properly, or the Fluke would misbehave, and it would obviously be very frustrating trying to use it. By the same token, if you're trying to repair one of these and you attach a logic analyzer, just be aware that might prevent the Fluke from booting up properly, and if you get that, just try unhooking the analyzer, see if it boots up. If it does boot up with the analyzer disconnected but not when you connect it, it does not necessarily indicate a fault. It's just the way these things tend to behave, so you might find you need to find a different way of attaching the analyzer. Okay, well, hope you found that of some help or interesting. As I say, in the next video we'll go through the firmware. I have pretty much finished reverse engineering this, and then I'll just demonstrate the basic initial behaviour of the add-on unit, and see how I'm going about developing the firmware, and also how I am reverse engineering the cassette hardware.